In the last season, we saw the evolution of artificial intelligence, from its beginnings to the present. This season, we will look at how an AI project is structured and some of the most common models. Today, information is everywhere. It is common to have data from different sources when we want to train a model. The first step consists of grouping, organizing, and reviewing this data to ensure it is of quality. Sometimes it is necessary to remove certain parts, reconstruct them, or even generate synthetic data using specialized techniques. Once we have achieved this, we must consider how we want to train our model with the available data. There are several ways to do this. For example, we could choose reinforcement learning, where the model learns from its own actions to maximize a reward. We can also opt for supervised learning, where the model is trained with a previously labeled dataset to learn to predict the correct output based on the inputs. This is ideal for classification or regression tasks, where the desired outcome for each training example is known. Another way to train our model is with unsupervised learning. Here the model explores the data without prior labels to discover underlying patterns or structures. This can be useful in situations where the categories are not known or there are no labeled data available, such as in clustering similar customers or in association tasks. As we saw last season, these models work with neurons. When new data enters, only the neurons related to the relevant features of those data are activated, according to what the model has learned during its training. For the same reason, different input data will activate different regions of our neural network. If we try to make a prediction without having trained it beforehand, the model will activate random regions, producing an incorrect output. Once we have decided how we are going to train our model, the next step is to define the values of the parameters that will shape it. These are the hyperparameters. During training, these values, such as the learning rate, the number of layers in a neural network, or the number of iterations, can be adjusted to optimize the model's performance and ensure it learns effectively without overfitting or falling short. While the model is being trained, it learns from its errors. This is where the backpropagation algorithm comes into play. This method allows adjusting the weights of the filters so that the network's predictions come closer to reality. During this process, we calculate the gradient of the loss function, which indicates the direction in which we should adjust the weights to improve performance. This is fundamental, as it allows the model to minimize the loss function that depends on the input and the expected output. By updating the weights in the opposite direction of the gradient, the model gradually reduces the error between its predictions and the real values. Moreover, to ensure that the model does not train indefinitely and reaches optimal performance, an error limit and an iteration limit are established. The error limit defines the minimum accuracy threshold that is desired to be achieved, while the iteration limit sets the maximum number of times the algorithm will adjust the weights. These limits help prevent overtraining and guarantee efficiency in the learning process. Before launching it into the real world, we must verify its efficacy with test data, focusing on metrics such as precision, which measures whether the predictions obtained are indeed precise, and accuracy, which assesses how well the model classifies or predicts in general. There are many other metrics that are essential to understand the model's performance in real-world situations. During training, it is also crucial to follow its evolution and adjust and improve the model as needed.